Hello and welcome to our short tutorial series, this time related to the topic of differential equations. Again, let me explain to you that this is just a short tutorial, just to get you acquainted with a few of the details. It does not substitute a formal course on differential equations. Right, so in the last lectures, I explained to you how important are the differential equations for engineering in general, and physics, and and chemistry, and biology. Everywhere we have to relate variations of quantities, and we have to connect those variations with some existent conditions that we normally call boundary conditions. And that's why differential equations are for express in a mathematical way quantities that vary one with respect to the other, right? And that we can map, because then we can understand the importance of external factors and everything. And I gave you many examples how the differential equations are important, especially in biomedical engineering. Nevertheless, it's not only solving equations that is important, because these differential equations are so important. It's important also to know how to build up a differential equation that represents a certain situation in nature, or in the laboratory, or in a different conditions that I created. Because that's the way to really, as I said, put everything I consider important in a mathematical expression. And we saw in the last few lectures how can be solved, what are the main methods that we should use to solve the differential equations. And I showed to you that there are many types of differential equations. Normally, differential equations, they make a relation between derivatives of quantities with their quantities or with other quantities and so on. And normally, when they have only derivatives of any order for functions that depend on a single variable, we call ordinary differential equations. And the ordinary differential equations are very common, and that's, they are among the ones that appear most in different situations. But it's not the only ones. We have also the non-ordinary, what we call partial differential equations, which are related to functions or with quantities that normally depend on more than one variable, like pressure, that's depending on temperature and density of gas. When we are dealing with gas, that's an example of function that's depending on up to more than one variable. And in that situation, when we want to relate variations, we end by constructing equations that are not ordinary, are partial differential equations. And speaking about the ordinary differential equations, we have what we call the order of the differential equations. And normally, the order of the differential equation is related to the maximum derivative, the order of the large derivative that we have. So if you have an equation that takes one derivative of some quantity, and that's all, it's called first order. If we have now equations that give the second order derivative or the third order derivative, so the highest derivative I do in the problem is what characterizes the order of the ordinary equation. And then I explained all this in the last lecture. And I showed to you that, well, there are simple and not so simple ways to deal with the differential equations. Today we're going to see some examples. And I told you that on the examples I'm going to try to give you highlights of important features related to the solution of the differential equation. Let's today deal with ordinary differential equations of first order. That means that only one derivative will appear in the problem. And I'm going to take a few examples so I can illustrate to you how we solve those equations. Normally, the first order differential equations, some of them is easy to solve, some of them demand some mathematical manipulation before it gets into a shape that's easy to solve and so on. Okay? And I'm going to try to do some practical examples. Of course, I'm going to speak a little bit about generalities, but normally it's nice to explain how to solve differential equations using examples. And the first example I took is what we call nuclear decay or radiative process. We all know that there are materials that I put a number of atoms together, like in a solid piece or in a liquid, it doesn't matter. And those atoms, they undergo variations. They will suffer what we call nuclei transformation or decay. So you have the nuclei of the atoms, they have the neutrons, protons, right? And they may decay. And when they decay, they emit radiation. Gamma radiation, beta particles, alpha particles, all those particles are very much used in biomedical application. You know, we all know the cesium radiation that emits, which is a kind of source of radiation for many things like radiotherapy or things like this. And the problem is simple, you know, we want to know how long a radiative sample lives before many of the atoms decays away and are something else. That happens with uranium, that happens with radio, happens with many things. So the problem then is very simple. We have a collection of any atoms. So anytime I look, I have some number of atoms that are able to decay. So those any atoms are atoms able to decay and emit to the outside radiation, particles, and everything. And we want to know how is the evolution of the number of active atoms as a function of time. We want to know how that happens. Of course, that number of atoms will only decay with time. If the number of atoms will only decay with time, it means that the derivative has to be negative. The derivative has to be in a way that is decreasing the number, not increasing. So we know that the rate of variation of those atoms has to be negative in any moment of time. And we know that if I have many atoms, each one has a probability to decay, so the number of atoms that decay is proportional to the number of atoms that I have in the sample. Right? So I have a sample that is radioactive, active. It's going to decay. The atoms will decay in something else, the nuclei, right? The nucleus of each atom will decay. And therefore, I want to create an equation that shows mathematically how is the decay of the atoms. Well, I want to know the velocity of variation of the number with time, which is the derivative of the number with time. Or this is the rate of variation of the number of particles. So in any instant of time, I have any atoms there. But I have also a decay rate. And the decay rate is proportional to the number at that moment in the sample. And must be negative. So we put a constant here. This constant has the dimension of 1 over time and must be negative. So this negative sign here is very important. And then I will assure that this physical constant is positive to somehow guarantee that the variation is negative. Always the number is decreasing. So as you can see, I already put many information on it. And to construct the differential equation, I use all that information. So here I have a differential equation of first order is ordinary, because I know that the number will depend basically on the time. So the number depends in a single variable. So it's an ordinary differential equation of first order because involves only the first derivative of the number. Okay, so let's solve this problem. That's a simple problem that teaches a lot. And basically, the variation of the number is proportional to the number. So that's the equation. And when that happens, we try to isolate. We try to put everything that's number in one side and everything that's time in the other side. So we try to isolate the two involved quantities in the problem. K is a constant, so it doesn't matter. Now, if I divide by n and I multiply and I put the dt here, the variation of the number of atoms normalized by the number of atoms has to be proportional to the variation of time. So this is another equation, but it's an equation based on infinitesimal variations on the number and in time. And it makes sense, right? Because it is basically obtained from here. Now, I know that my number, so now that I have this, I have a differential part here and a differential part here. I can integrate both sides of this equation. So by doing an integration, so from here I go to here, by doing a single operation, an integration. By doing the simple integration, I have that the integral of the relative variation of the number must be equal to the integral of the increment of time. We all know that the integration is, you learned that in other courses, is basically the sum of all those increments. So the sum of all the relative increments has to be proportional to the total time considered in this decay process. But now we know the rules of integration. We know that the integral of a variation of anything normalized by that thing is the logarithm of that thing. So this first integration provides logarithm of n. This is the primitive, right? I'm not integrating limits because I'm going to use the boundary conditions, some initial conditions to find out whatever is the constant that appears in those integrations. And the integrations of increment of time is time. And of course, in this process of integration, I end up by having a constant, which is the indetermination, right? Because for this not to appear, I should do the integration with limits, but I didn't do. I just did a generic integration, an indefinite integration, and here it is. Right? But I have one condition. And the condition I have that is in t equal to 0, n equal to n0. This is a condition. It's a very important boundary condition, initial condition. So if I make t equal to 0, the number is n0. So when I make this equal to 0, this is n0, therefore c is logarithm of n0. Right? Because if I take this out, t equal to 0, this disappears. And then n became n0, which is the initial number. So by doing that, I discovered that this constant is logarithm of n0. And then I pass this logarithm here, is subtraction, and then became division. Or I don't need to do that, I just keep logarithm here. And then I invert the logarithm. So from these conditions, I obtain that c equal to log n0. Right? Therefore, by inverting the logarithm, which is an easy operation to do, I get the total number as a function of time. The total number of particles as a function of time is an exponential, which has as an exponent this constant here, right? The constant that appears here, which has unit of the inverse of time. So so with this, I guarantee that the exponent has no units, which is very important, right? There is no exponent of hours. Well, there is exponent of number, a dimensional number. So you have to be careful with that. So I find out that the decay is exactly like a exponential. So I start with the number. So if now I make a plot, what's going to happen here, right? I'm going to make a plot so you can understand. So if I draw what's going to happen with the number of atoms as a function of time, it's going to start in some n0 and it's going to decay. Decay, and eventually it's going to go very close to 0. And this is a proportional to this constant, which is the decay constant, right? Which has the dimension of inverse of time, and the inverse of the constant has dimension of time, and that represents a time that is important on the evaluation of the lifetime of the sample of n atoms. So this is an example of ordinary differential equation. So if you put 1 gram of cesium-137 in your reservoir to have a radioactive source that will produce radiation for your radiotherapy and so on, you have to know what is this constant, because you're going to know when that sample is ending, right? And to recharge and things like this. So that's a nice example of a differential equation. Normally, when we deal with differential equation, that is what we call the separable equations. I did that in this practical example of the radioactive decay. But I want to be a little more formal to explain to you that this is a generic way of doing. Normally, when I have a differential equation of first order, we're dealing with first order differential equation. Do not forget, please. Right? And then we can separate. Normally we have things like this. And when things goes that way, we can make a separation of equations. We make in one side the equation to have a full dependence of one of the variable. Here is the y, right? And on the other side, we make the full dependence in x. So normally equations like this obey relations like that. They have an independent function and they have another function that multiplies the derivative of the y, which is we want always to find what's the dependence of y with x's in those differential equations, right? In many cases, I can separate the two equations. I can put everything that's y in one side and everything that's x in the other side. And when I do that, I'm in good conditions, because you see, for this to be true, this has to be true always, means that I can treat independently this part and this part, but they must be equal all the time. So, correct? So what I do then is integrate both sides, and by integrating both sides, I have here something that will depend only on y, and here something that only depends on x. So I have then now, I transform my equation in an algebraic equation with dependence in x and y. Right? Because I have an equation that there's no more derivative. I run away with the derivatives or the differential variations. and I end it with an algebraic equation. Normally, this equation that I'm showing here, this equation here, is an algebraic equation. So that equation here became an algebraic equation, which means has x and y's, and I have to solve it to find out what is the dependence of y with x and vice versa and so on. Let me give you an example of this. Imagine that we construct a differential equation, and it shows that dy dx equal to minus 4 over 9x divided by y. I could put this in another way, just saying that 9y dy dx, right, plus 4x equal to 0. You know, that's equivalent to this equation, the same equation. But here I left that way because it's clear that if I multiply the y here and the dx here, you know, I still have a relation between the variations of y and x, but now expressed in a single sentence like this, like the way we said here. Everything that's x will be on one side, everything that's y will be in the other side. Right, and when I do that, of course I will get y times dy is equal to minus 4 over 9 x times dx. And now I integrate. So I already made the integration. So I make the integration in both sides. Y dy, what's the integral of y dy? Is half of y squared. And what is the integration of x dx? Is half of x squared. And of course, because this is an indefinite integral, you have to end with a constant that can only be solved when you give the initial conditions, when you give some initial conditions for that. Okay, you see, you can take the 2 away, you can put this 4 under the y, and the 9 it keeps under the x, and then you get a very nice equation here. You may recognize what the equation is this. This equation is the equation of an ellipse. So the function x, no, the function y of x is exactly the curve that generates an ellipse. Of course, here, this square is the short axis and the long axis. Actually, this ellipse is elongated on x, right? And shorter in y, because y is 2, 4 is 2 square, and 9 is 3 square. So I get this. So it's very interesting that the solution of this differential equation in a graphical representation provides an ellipse for us. Sometimes it's very useful to recognize what is the graphical interpretation because, you know, it makes sense in many things. After all, when you do this, you're going to see that this is a very interesting variation because dy dx, which is basically this, will change sign depending on what is the range of value of x because of the negative value. And this is very interesting. And of course, as we see, only if the c equals to 0, if c is not 0, we're never going to have 0 as part of the plot, right? I mean, we may have x equal to 0, and then y we're going to have a value. Or we may have y equals to 0, and then we're going to have x another values, but never both zeros here, you know. And this is interesting and comes from separating. I separate the equations, put everything of one variable in one side and everything of the function or the other variable in the other side, and then I'm able to integrate and comes out with a very nice solution for that. That's another example. You see, you have to keep your attention to cases where that thing can be done. And sometimes it does not look easy, but it's very common that you can. You can separate the functions. You can put the functions in two sides of the equation. This is like separable equations. I made one equation. Why we call separable equations? Because actually, this is like this being a constant and this being a constant, this being a constant, this being a constant. I can, and they are the same constant. So, but let me consider another example of a first order differential equation before I go to another practical example. And this is, suppose I build up an equation, and the equation tells me that the function I'm looking for, which is y, I don't know y of x, this is always what I'm looking for. Y of x is something that obeys this mathematical relation. dy dx is 1 plus y squared. Oh, there are many phenomena that may obey that, right? And here you see that I can say that this whole thing is like multiplying by 1, right? Therefore, if I divide everything here, then I can separate a relation between the variation of x, variation of y, and x and y in different terms of the equation. So if I divided this by 1 plus x squared, and then I put the dx here in the 1 that was there, I get an equation exactly like the one I said I should have to be able to integrate and should be able to apply what we call here the separable equation method, which is basically put everything that's y on one side, or f, you call what you want, and everything that's x in the other side, or t, or whatever is the independent variable, and then make an integration in both sides. We all know that if you have a equality, a mathematical equality, the integration is also true. And then I come and I make the integration. The integral of dy over 1 plus y squared has to be integral of dx, which is x. Integral of dx is x, right? Everybody knows that. Integral of dx is x. But you need a constant here because we don't know what are the initial conditions, or it must have a boundary condition that determines well this constant. This is the particular or the specific solution. This is a generic solution. Depends on the initial conditions that you give, you're going to have a different value for the constant c. Because it is only determined, this constant c, arbitrary constant c, after you establish the conditions, the initial conditions. Now, this integral, you may do it in many different ways. There are many ways of doing integral. I'm not covering this in this course, but an integral of this gives you the arctangent, or the tangent minus 1 of the variable. So this integral results in tangent, the inverse tangent, right, or the arctangent of the quantity y. And here ends by being x plus c. If the arctangent of y is this, means that y is the tangent of this, right? Because here I say that the arc which tangent is y is this. So means that this is the tangent of this, right? Therefore, I have the solution for this. The solution is exactly y equal to the tangent of x plus c. If I impose there, say, look, when x is equal to 0, y must be 0. Then I come here and I say, well, when this is 0, this is tangent of c. But this has to be 0, so c has to be 0. Or some multiple numbers of pi or minus pi or so ever, or 180 degrees or something like this. Okay? But, you see that the constant will depend on the initial conditions. That's another example of solving first order ordinary differential equation, right? Using what we call the separable variable approach. Very good. Okay, so you see we saw some examples, but we should continue with different examples. And there are some very nice practical examples that I want to give you. And in the next lecture, I will give you more examples on this relation, on this topic, so you can get more acquainted with examples, how to solve those equations, and do yourself when a problem comes up. See you in the next lecture.